Welcome to Making and Treating of Steels course. Today I am going to introduce Unit 5, which broadly includes continuous cooling and time temperature transformation of alloy steels and subsequent steel making processes, and which also includes various common heat treatment process, annealing, normalizing, hardening, and some of the thermomechanical processes such as cold working, hot working, which includes extrusion, forging, rolling process, and some of the numerical problem sections, material balance or charge balance, feed calculations, all the steel making problems covered, and continuous casting numerical problems, tundish metallurgy, ladle metallurgy, and quantity volume based calculations includes Unit 5. And as you know from the physical metallurgy topic, this is iron cementate diagram, or cementate is nothing but Fe3C, iron carbide or iron carbon diagram. There are various names which broadly are followed. This is iron and iron carbide diagram. This particular point is eutectic point and eutectoid point. This is austenitic region. This is entirely liquid. This is combination of, this is a delta region, this is the alpha region, and this is combination of alpha plus cementate perlite region. This perlite is equilibrium perlite region. The composition, this is 0.216 carbon, this is 0.8, this is 4.3, this is 6.7 percentage of carbon, and these things are known to us. If you take this particular steel, and it is broadly studied that if you take eutectoid steel, above this is entirely austenitic region. Can you convert this particular austenitic steel into various phases microstructure with respect to the hardness for various applications? It doesn't mean that the steel is coming from the secondary steel and continuous casting, only suitable for all applications for further thermomechanical heat treatment process. There are few steels are developed by taking consideration of the time temperature transformation diagram or continuous cooling transformation diagram, the material developed by those steels, which we are going to learn in this particular topic. The time temperature transformation curves, it also has other name isothermal. Constant temperature is followed and steel is transforming from the austenite parent phase. Mainly eutectoid steels are taken and studied under this particular section, and various carbon composition of steel can be taken with respect to the eutectoid steel and can be studied and transformed, application and suitable properties, how those things. Let us know more information about this thing. This particular temperature transformation controls from the main decomposed product phase of austenite. Austenite is decomposed into other phases such as bayonet and martensite and non-equilibrium perlite, which gives resultant properties of steels with respect to the various applications. Wires, bake hardened steel, transformation induced plasticity steel, twin induced plasticity steel. So all those things are studied by these particular curves, and mainly the kinetics involved in austenitic transformation. Austenite, parent austenite phase is transformed by maintaining a constant temperature, gives very good statistics when you compare with respect to the continuous cooling. Continuous cooling also, with range of cooling rate, you can transform from the austenite to martensite, perlite and bayonet. Comparatively reproducibility and study is not optimized. When you compare with the TTT transformation, it is completely optimized and it is witnessed to the standard applications, the phase transformations are studied, and constant temperature transformation also referred as I mentioned, isothermal constant temperature, and which basically developed by Davenport and Bain firstly TTT diagram for eclectoid steel, and this is determined and given the end product perlite and bayonet portions are shown in the TTT diagram, and later it was developed by Cohen and is included another phase, starting point of martensite, finishing point of martensitic temperatures are included. Then combination, now we are studying the combination of the phases which are termed as a time temperature transformation diagram. There are number of methods to determine the TTT diagrams, drawing the TTT curves. The broad popular technique is salt bath. You can maintain the constant temperature and you can vary the various cooling mediums also, and you can get the various phase transformed, and with observing the microstructure at different temperature and time level and correlating with the oddness. This is how these particular graphs are fitted and standardized. And there are many other techniques such as dilatometry, XRD, thermal measurement techniques, density measurement, thermodynamic predictions. These things are good for the knowledge sake. Now, but it is very important that at every composition, not only for the eclectoid steel, it need to be developed for a different composition of in the entire iron and iron carbide diagram. It has demand. So there are many studies are going on in the present days. These are the experimental setup to construct the TTT diagram. Salt bath at higher temperature, maintaining the higher temperature, austenization treatment. Parent phase is austenate and converting into the various phases perlite and bayonet, and lower temperature treatment. This is how the sample is maintained and fitted into the fixtures, and this is closed and operated at this particular. This is other instrument, dilatometry equipment. This particular specimen is fixed. You can do lower temperature and higher temperature, and with respect to the time you can draw the curves, temperature, maintaining the constant temperature, and time using the dilatometry. This is most of the, instead of nowadays, this is the modern technique. This is becomes old technique. You need to notice those particular things. This is example TTT diagram for the eclectoid steel, taking exactly the 0.8% of carbon. This is entirely austenate. Above 723 it is eutectic temperature, and at this particular eutectic temperature, for example, if below this, if you maintain this 600 degrees Celsius temperature in the salt bath and temperature is constant, and go for the time, and as you proceed for the time, you will realize to see coarse pellet structure at this particular 650 and 550, fine pellet structure, microstructure is given the signatures. And another thing, at 500 if you maintained constant temperature, you will see bayonet, upper bayonet, lower bayonet, upper bayonet feathery structure, lower bayonet acicular structure. You will realize to see this is for the lower bayonet, this is for the upper bayonet structure, and below this you will see, if you maintain this particular temperature, you will realize to see constant temperature martensite needle like structure with varied time, and this particular curve is continuous cooling line. If you do fast cooling at this particular temperature, avoiding these particular curves, this particular nose of the C curve, if it is been avoided, this is the perlite starting temperature, perlite finishing temperature, this is martensite starting temperature, martensitic finishing temperature line. This gives a good idea, and that is why it is included. Cooling curves are non-isothermal. This martensite phenomena is whereas perlite bayonet are isothermal phenomena, whereas martensite formation is non-isothermal. By fast cooling you will realize to see, you will not observe this TTT curves. In TTT curves you will not see martensite, in the cooling curves you will see martensite. That difference also one need to notice. Now give your opinion that bayonet and martensite does not appear in equilibrium diagram such as iron carbide diagram. Instead of these things exist in the TTT diagram. Is it true or false? Please give your opinion.